Okay, well in some ways this is the first case of the embedding problem. The embedding problem in this context means how many different ways are there to embed manifold A into manifold B. The fact that the first case of the embedding problem has a section of the library named after it maybe tells you something about the embedding problem, although it's not perfectly indicative. Some cases are not this hard. Second reason, maybe I won't write this one on the board, but I'll mention for the sake of anyone who's interested in this sort of thing, that a second reason knots are interested is because many things in the real world are in fact knotted. Third reason, well, knots are sort of very concrete and tractable. I can get my hands on them, I can make them out of ribbon if I like, I can certainly draw myself pictures of them, but they're deeply connected to 3 and 4 manifold topology. When they say that, mean that they care about dimensions 3 and 4 primarily. In 1 and 2, we sort of understand everything that's going on. In 5 and 4, in 5 and above, there's more room to maneuver, and so many things can be made sort of standard. 3 and 4 are sort of the most interesting and mysterious to us in some ways. So, and why are knots so connected to 3 and 4 dimensional topology? Well, one of the main reasons is the surgery construction. So let's talk about the relationship of knots to 3 manifolds. Okay, what's the surgery construction? Let's say I've got a knot in S3. I'll draw 2 different knots. I'll draw an unknot and I'll draw a trefoil. What I'm going to do is I'm going to cut out a little torus around my knot, a little solid torus, and I'll just cut that torus out of my manifold. There was some mention of colored chalk.
It's in the envelope.
It's in the envelope. Thank you. Great. Distinguished curves, a meridian, and the longitude. Here can be my longitude. Here, if I draw my longitude just straight onto the blackboard, it'll end up twisting around the knot itself, so I'm going to have to add some extra turns to untwist it, so I'll draw the correct longitude. But I sort of won't explain why it's the correct longitude. One, two, three. Okay, so what we do is we cut out this tiny torus. And now we've got our manifold with a torus-shaped hole in it and our torus, and we're going to reglue it in differently. We're going to reglue it in so that a meridian, the blue curve on the torus, goes to a curve that winds 2 times around the longitude. And p times around the meridian. be P over Q of K. So I cut out a torus, I reglue it indifferently, I get some 3-manifold. So maybe a couple of examples of things obtained via this construction that you may in principle have heard of. So for example, if I do P over Q surgery on an unknot, I get the lens space LPQ. If I do +1 surgery on this trefoil I've drawn, and then that's an oriented 3-manifold. If I reverse its orientation, which is the same thing as having done instead -1 surgery on the same knot with all the crossings changed. So notice that I've changed which strand is uppermost in the crossings here. So that's the point creating homologies here, which is a very famous example. And fun fact, if I did +1 surgery on the figure 8 knot that I drew, for 1, that would be the same as if I did -1 surgery on my original trefoil, and that's also a famous example that we'll get another name for later in this talk. Okay, so, and why is this, okay, so this is a way of constructing some 3-manifolds. Now we have some named 3-manifolds. That's very useful for talking about them. And why is this so important? Well, there's a theorem of Licorice and Wallace from the 60s that any 3-manifold I want can be constructed, well, not by surgery on a single knot, but surgery on some collection of knots, possibly not linked with each other. So the theorem of Licorice and Wallace some disjoint union of multiple copies of S1 into S3. So here's an example of a link. That's the hot link. Okay, and indeed I can be more precise than that. I can require things about the individual components. I can restrict what coefficients P over Q I need to take in the surgery. This is quite powerful. So this tells us why we care.
And still get every 3-manifold?
Oh, pardon?
And still get every 3-manifold?
Yeah, so in fact, each of the individual components can be an unknot just linked with each other, and you can also take the coefficients to be either 0 or 1. So just by sort of following yourself along in what the construction, what Licorice construction gives you. Okay, so that's why knots or 3-manifolds are linked. Those are some of our objects to study. Now let's ask ourselves a question. Why should I think about two 3-manifolds as being importantly equivalent to each other? Well, there's diffeomorphism. That's fine, that's very granular. Maybe I want to be a little bit more flexible. So I'm going to think about my 3-manifolds being related by bounding a 4-manifold. And then I'll think about what words I need to add to that sentence to produce something sensible. So I'm going to think about, maybe I have a 3-manifold here. And a 3-manifold here, and they're related by co-bounding a compact 4-dimensional manifold. This is a cobordism. About things of this approximate form as equivalence relations between 3-manifolds. If you've never seen anything like this before, maybe you're supposed to think to yourself, why would it occur to me to do this? Well, one motivation is that, space-time is a cobordism, although not quite one of this kind. So, you can think of yourself as I have a 3-dimensional space and I move along time and I get to another one. That's sort of a very big motivation. We can perhaps think of better ones. So, alright, so maybe I want to relate my 3-manifolds by 4-manifolds. So D2 across the circle, S1, and we replaced it with some other copy of the torus glued in differently, S1 cross D2. And I can think of that as being the boundary of a copy of D2 cross D2, a two-handle for those who know the word, filling in between these two tori. And anyway, the upshot is that a surgery diagram for a three-manifold just constructs a cobordism between it and S3. So that's not good. That would be very boring and I would have to go home early. What else might it occur to me to do? The next thing you might think of is maybe I want to look at cobordisms that are sort of simple with respect to some of my favorite invariants of topological spaces. So the next question you might ask yourself is, well, maybe I'm supposed to be looking at H cobordism or homotopy cobordism. One of the most famous open problems in four-dimensional topology. So I'm not going to try that today because I want to end this talk at a reasonable time. So too hard in the smooth case. It contains the smooth four-dimensional concrete conjecture. These are equivalence classes of maps of spheres into the spaces. Alright, so what am I actually going to consider? Well, if you're a topologist, if homotopy fails you, maybe you go to homology, which is a sort of somewhat more flexible and easier to deal with invariant. And indeed, the relationship we're going to consider, which turns out to be at this very nice level of something you could ever work with, but still contains lots and lots of geometric information, is going to be so-called homology cobordism. Questions, comments, concerns? All right. Equivalence classes of embedded submanifolds. Okay, so I want for those who know what homology is, I want the inclusion on homology and either end to be an the inclusion on either end to give us an isomorphism embedded submanifolds. So this is a set of groups H0, H1, H2, H3. H1, for example, consists of embedded multi-curves up to considering them equivalent if they co-bound a surface, and so on for higher dimensions. All right, so that's the thing I want to consider. And in fact, just for today, I actually want to cut my set of 3 manifolds down. Now that I have homology, I'm going to cut myself down to considering the set of 3 manifolds that have the same homology as the 3-sphere. So things that I can't tell apart for the most basic 3 manifold using this tool. So that's going to be 3 manifolds, Y with the same homology as S3. Okay, so it's not quite true that that's the same thing as saying every embedded submanifold is a boundary, but if you've never heard of the idea before, then it will give you the right idea to think about. All right, and we're going to study the set of such manifolds. So manifolds that I can't distinguish using homology from the 3-sphere, up to the equivalence relation of homology cobordism. So I'm going to study the set of things that are oriented. Remember I said these things come with an orientation. Integer homology spheres up to the relationship of homology cobordism. So I'm going to look at smooth, compact Floer manifolds between them, such that on either end, inclusion induces an isomorphism on this algebraic invariant homology. Okay. So, I said that had to be smooth. Maybe I'll mention, so as many people here may know, topological and smooth manifolds are quite different categories. And this is going to need to be smooth, for example, because a result of Friedman implies that if I allowed topological form manifolds there, the group would be trivial, and then I would again have to go home early. And I just said group. I haven't sort of justified that to you yet. Let me mention that this is a group. The identity is S3. And the group operation is connected sum. What's connected sum? Well, it's hard to draw 3 manifolds, so let me draw you the connected sum of 2 manifolds, and then you can go ahead and extrapolate. So here, let's say that these are hollow tori, perfectly good 2 manifolds. What am I going to do? I'm going to cut out a little disk on both sides, leaving myself an open circle, and then I'll glue those 2 open circles together. And that's your connected sum operation. So more generally, I cut out a ball in each manifold, leaving me the 2 spheres, and I glue those 2 spheres together. It's by no means obvious that this is a group. You have to sit down and check that you have, well, mostly the inverses work the way you would like them to. These are by switching orientations. But indeed, you can check that, and it most certainly is a group. Okay, so that is our object of study, the group of 3 manifolds that are simple enough that they can't be distinguished from the 3-sphere using one of our favorite topological invariants homology, up to cobordisms that share the homology at either end. Another way of saying that is up to cobordisms that cannot be distinguished from a cylinder S3 cross I using this invariant homology. So fairly simple 3 manifolds up to fairly simple cobordisms, and yet there's going to be a lot of information here. Maybe I should give you some examples of things that are in this group at this juncture. some equivalence class in this group. Maybe something that's not a surgery. We could look at a rescored sphere. What is that? Well, I'm going to look at sigma PQR. P, Q, and R being coprime. Which is the intersection, this is all going to be happening in C3, of Z1 to the P plus Z2 to the Q, plus Z3 to the R being 0. Pardon?
I just asked Jack Milner if he knew that one.
I feel like maybe he might have heard of it. Intersected with a small sphere about the origin of spy sphere. For the sake of our sanity, let's check some dimensions real quick. This is in real dimensions. This is 4-dimensional, this is 5-dimensional, and this is 6-dimensional. So okay, I do expect to get a 3-dimensional intersection there. That's good. Maybe I'll mention, in the spirit of mentioning anything in this talk that's not a surgery on an individual knot, but rather you need a link, maybe I'll mention that sigma P 2P minus 1, 2P plus 1, for P greater than or equal to 8 is not a surgery on a knot. That's not the first example, of course, that's not even the first integer homology sphere example. It just happens to be an example that's easy for me to name to you. That's due to Hom, Lidman character. Okay, maybe let's mention an example. So I said an example of something being trivial in theta 3z while we're on in example land. So I said this is integer homology spheres up to some equivalence relation. So maybe we'll have some examples of triviality. Oh, I was actually going to name a couple of those response spheres while I was over here. We'll get back to examples of triviality in just a minute. I wanted to mention sigma 235 is our Poincare homology sphere again. And sigma 237 is that +1 surgery on the figure 8 knot, -1 surgery on the right-handed truffa that I mentioned a minute ago. Figure 8 knot. Okay, and then I was going to tell you some things that are trivial in the group I care about. So sigma 257 is a famous example of something that's in the same equivalence class in S3, that's homology cobordism to S3. And your favorite 1/Q surgery on the following knot. We're really pushing it on my artistic capabilities, but this should be the correct knot. There we go. The so-called stevedore knot is another example. Okay, so I've told you this group is an object of study we consider interesting. It's our group. You could ask me what things we know about its structure. Let's talk about some things we know about its structure. Okay, so until the 1980s, not a lot. One of the sort of main things known was the existence of the Miller-Rothman homomorphism, which is a surjection from this group onto Z mod 2Z. So an example of something that's in the pre-image of 1 is sigma 235, a Poincare homology sphere. Okay, and I was not alive to this point, and some members of the audience were, but I'm reliably informed that if you had been going to your topology seminar in the 70s and you'd said, oh, my conjecture is that that map will turn out to be an isomorphism, well, you would not have been laughed out for saying ridiculous things. That's what they tell me. However, as it turns out, you would have been wrong. So in the 1980s, we got gauge theory, and that gave us a whole bunch of new tools for studying these manifolds. So it's a consequence of Donaldson's theorem, the sort of big first application of gauge theory to low-dimensional homology, that theta 3z is infinite. Okay, so in particular, the equivalence class of sigma 2, 3, 5 to the n is not the class of S3 for any n greater than 0. Okay, and Fintelschel, Stern, and Veruda in fact proved that theta 3z is infinitely generated. So there is a z infinity subgroup inside of it. Okay, in 2010, Frischau showed theta 3z has a z Sunend. Okay, let's all recall that having a Sunend is stricter than having a subgroup. It means you decompose as a direct sum, so these two statements make sense next to each other. Okay, in 2013, Chipper and Manolescu showed that, I'm going to say this in a way that'll seem sort of dry, and then I'll explain why it's important. There do not exist elements y of order 2 in theta 3z with Rockland invariant 1. Why is this a thing you would want to show? Because via previous work of Gluski, Stern, and Matsumoto from the 70s, this resolved what were at the time the remaining cases of the triangulation, outstanding cases of the triangulations conjecture. Okay, I'm not going to explain this whole story right now, but I'll just mention that this is a fairly big deal, and say out loud the words, this showed that there exist topological manifolds in every dimension greater than or equal to 5, which do not admit triangulations. A triangulation is a homeomorphism to a symmetrical complex. People usually at this point when I talk about this say something like, wait, what does dimension greater than or equal to 5 have to do with dimension 3? And the answer to that question is the obstruction that Gluski, Stern, and Matsumoto were looking at in principle exists in every dimension, but it's only possibly non-trivial in dimension 3, and that's because 4-dimensional manifolds, the cobordisms we're considering, are so difficult. Okay, and then, and I'll mention that this is the inspiration for all of the new work that involves me that I'm going to explain in this talk. And then, quite recently, Dai, Hom, Stoffregen, and Schramm just a couple months ago showed that theta 3z has a z infinity subend. And in fact, I'm telling this in a somewhat ahistorical order. So this is using constructions of the Chyprion that will be mentioned later in include A, no, B, there's no torsion of Rockland invariant 1, but there might be some of Rockland invariant 0, and I think a sizable contingent of shrug. Another question, does theta 3z have a straightforward generating set?
It could be a Z4 with Rockland invariant 1, no?
Yes, there definitely could. It's a popular conjecture, not a popular theorem. Yeah, so we don't know what's going on with torsion. 2, does theta 3z have a straightforward generating set? So, in fact, the candidate straightforward generating set is a general class that includes the Brieskorn spheres that I introduced for you, the Seifert-Fibert spaces. It's well known, it's not well known. It's a relatively recent theorem, just a few years ago due to Maxtoff-Reagan, that that not every integer homology sphere is homology coordinate to a Seifert-Fibert spaces, but they could still Seifert-Fibert space, but they could still generate the group. We also don't know if every class includes a surgery on a knot. So I told you not every three-manifold is surgery on an individual knot, not every integer homology sphere is surgery on every individual knot. But we don't know if every integer homology sphere is homology coordinate to a surgery on a knot. That's also an open question. So you see there are many things we don't know. Okay, so in the remaining 20 minutes, it's time to maybe talk about some invariants from Floer theory, some of which played a role in some of the results I've told you about. Okay, so let's talk a little bit about Heegaard Floer homology and a new invariant of homology cobordism called connected Heegaard Floer homology. We use that to construct a higher dimensional auxiliary symplectic manifold. We take some version of Floer theory, which is another awesome tool that's from the 1980s that's had lots of great consequences in low-dimensional topology. We take the Lagrangian Floer homology, it's called, of that setup, and by a minor miracle, it spits out a topological invariant. So that sentence is just to note that the symplectic geometry goes here. But we get to ignore that for today. Let me tell you what this module looks like. Well, in fact, it's the homology of a finitely generated three-chain complex over a principal ideal domain. So that imposes quite a lot of restrictions on its own, and then there are some more from the actual setup itself. So as it happens, HF minus of I, in our case, always looks like a single copy of F adjoining U in some degree D. What does this D mean? So notice that this module looks like 1, U, U squared, U cubed, etc. This D here is just the grading of the element 1. That determines the gradings of everything else because I already know the grading of u is minus 2. Plus some number of copies, well, some number of pieces that look like f adjoint ci over u mod u to the ni from I equals 1 to k. In fact, the fact that I had to look like some pieces like this and some pieces like this is pure algebra. The fact that there's only one of them is an actual theorem. Okay, and this is the so-called U-torsion submodule of the theory. Called HF red. Okay, so we could have perhaps some examples. We could have S3. Its HF minus is a copy of F adjoining U and grading 0. We could have the Poincare homology sphere. Its HF minus is the same thing but in a different grading. We could have the other Rees-Korn sphere. That was the subject of that surgery coincidence I mentioned. Now I'll actually get something from the second part of the theory. I'll get a copy of F in grading 0. I'm supposed to think of F as F adjoin U mod U to the first. I could get 2 copies of that. And I get the same thing, F0 U, but now I'm going to have 4 things. F0, 3 copies of F in grading 0, and 1 copy of F in grading minus 1. I will come back to this table in a minute.
Does this homology have a ring structure?
Pardon?
Does it have a ring structure?
It does not have a ring structure. It's just a module over F adjoin U. Maybe this is a good moment to mention that Heegaard Floer homology is not a homology theory, for anyone who was wondering that. I'm sorry about that sentence. Which is to say it's, for example, not isomorphic to singular homology. Alright, so we can ask the question, what does HF minus tell us about theta 3z? Okay, so there's not that much information going on here. There's this number, and there's these numbers, and there's these numbers, and we're not actually going to use those for anything today. So the first thing is, what does the free part of HF minus, the single copy of F adjoin U, tell us? The only information is this number D, but that does turn out to be information by work of Ojibwa and Zotto. D, in fact, gives a homomorphism from theta 3z to the even integers. This is the so-called correction term, and it has in fact had lots of applications to homology cobordism and to other things in 3-manifold and not in 3-manifold theory and not theory. So that's a great answer to that question. We could also ask, what does the U-torsion part tell us about theta 3z? Okay, and if you ask yourself this question, you will very quickly notice the following thing. This part right here is not a homology cobordism invariant. I can just have 2 3-manifolds that are homology cobordant to each other and have different HF ranks. All right, well, I guess that's not how I'm pursuing this question. So the first observation is this isn't an invariant of homology cobordism. homologies associated in manifolds Y, which are homology cobordism. And here's a theorem. The theorem is the whole thing is not a homology cobordism invariant, but some submodule of it is. So there is an F adjoining U module, graded as it happens. The connected homology of Y, which is isomorphic to a submodule of HF red. And whose isomorphism type is preserved by homology cobordism. Okay, so some submodule of this is actually preserved, and we call it the connected Heegaard Floer homology. The connected refers to being sort of connected to the free part by some map. Alright, and this submodule is generated by everyone's most beloved strategy of getting an invariant. I have a giant set of things associated to some object. Why don't I try and take the smallest one in the class? So, let me tell you a couple of words about the construction. So, the construction uses so-called involutive Heegaard Floer homology of Manolescu and I from 2015 and elaborated by me and and E and Zemke the next year. The key point about this theory is that it looks at a map from CF minus to itself that's very close to being an involution, chain homotopy equivalent to an involution. Okay, and then there's lots of things you can do with that. You can construct the theory we actually called involutive Heegaard Floer homology, but the thing we're going to do today to get connected is we're going to look at pairs consisting of the chain complex and this map. And then we're going to look at them up to an algebraic equivalence relationship. So algebraic equivalence relation that's, well, it's not as strong as chain homotopy equivalence. It can't be, otherwise we wouldn't be preserved along homology cobordism. It's some weaker thing that respects homology cobordism. Okay, and then the HF red submodule of the smallest such pair. So the smallest thing in the set of equivalent complexes together with maps is the invariant. Okay, there are a number of unanswered questions about that word smallest involving what do you mean and how would you know that that was an invariant. I'd just like to note that I'm not answering any of them, and you're right to ask. Okay, maybe I'll fill in a couple of examples of this theory in my table and tell you a first proposition, and then maybe after that a last proposition. So let's have the connected in this column. Okay, so
if you're not going to tell us what it means to be smallest, can you give us an example that gives an idea?
So what it means is maps between complexes that are equivariant up to homotopy with respect to iota, and which preserve the free part. And what I'm going to do is take maps from these complexes to themselves, which essentially look like if I can possibly do an equivariant change of basis that separates a piece of my complex from the part that generates the free part, I throw that away. So I maybe throw away some actual generators of my homology that way, and I keep everything that I can't separate from the main tower. Was that a helpful explanation at all? Allow me to give you I'm also happy to draw a chain complex immediately after the talk and show you if you prefer. So here, well, there's no HF red, so we just get trivial connected. Here, we keep the entire HF red. Here, I actually don't keep all of this. Some of it's not going to be preserved under homology cobordisms. I can separate it from the main part and throw it away. In fact, I end up with a two-dimensional theory. Maybe I'll have one further example here. If I did -1 surgery on T2 4n plus 1, remember we learned what T2, any odd number was at the beginning of this talk. I'm not going to write down its entire HF menace, this is big and complicated, but I will note that it's connected is a copy of F adjoin U mod U to the n. So here finally I'm getting something without a trivial U module structure, starting and grading 0. Okay, maybe let's have a first application on a proposition. If the dimension of HF connected of Y, what do I mean by that? This is an F adjoin U module, but in particular that it's an F vector space, and I can think about its dimension there. If its dimension is 1, then the equivalence class of Y has infinite order in theta 3z. Okay, so remember I said we're interested in questions of torsion in theta 3z, so perhaps this sort of thing is a little bit interesting. And for a second application, so we can also use this to filter theta 3z. What do I mean by that? I'm actually just going to do the thing and then it will become clear what I mean by that. So let's let P be the set of subsets of n with a subset partial order. Subsets, we'll call them P. And let's let Fp, for any given subset P, be the set of classes Y in theta 3z such that the connected homology of Y looks like, well, it has to look like a bunch of copies of F adjoin U mod U to the ni because it's a subset of the U torsion submodule of submodule of the U torsion module of something else. I'm not putting in any gradings here because they don't matter. All I want is that these numbers in the coefficients are in my subset P. Okay. And the proposition is that this is a filtration. What do I mean by that? What I mean is that firstly, Fp is a subgroup of theta 3z. This is actually not very hard. Anyone in this room who's had a first algebraic topology class would be able to do it quite quickly. 2, if P1 is a subset of P2, then Fp1 is contained in Fp2. guys is the group itself. Okay, so this sort of separates out theta 3.
What does one say?
It's a subgroup? Pardon?
It's a subgroup.
Yeah, it's a subgroup. That's what it says. So in particular, some fiddling with the Knuth formula and the correct notion of equivalence of complexes returns that very quickly. Alright, so this separates out theta 3z into sort of levels associated to the subsets of the natural numbers. One sort of very quick corollary of this structure.
How does this behave under connected sum, you know?
The answer is interestingly. May I state this and then come back to that? It's not. So the answer is it's a submodule of the thing you get if you just took the Knuth formula, is the short version. So the corollary is let theta n be the group generated by 1/n surgeries on knots k, having genus. The genus is a measure of the geometric complexity of a knot, for those who are not familiar with it, less than some capital N. Then this group, which is surgeries on knots of sort of bounded some measure of geometric complexity, is never all of theta 3z. Okay, and the proof of this, which I'll just say out loud because I'm out of time, is that one can show pretty quickly that this lives in bounded filtration, level, and one can show pretty quickly that this does not exist in any bounded filtration level. For example, by considering this example, notice how the ends are getting very large. Okay, I'm out of time and I'm out of words, so thank you for your attention.
Questions? How does it behave under connected sum?
So how does it behave under connected sum? Okay, so maybe I've got a minimal complex in one equivalence class and a minimal complex in the other equivalence class, and I tensor them together, and that's not necessarily minimal. Maybe the minimal thing is actually smaller, but certainly whatever I get from the Knuth formula in that case contains the connected homology, which means that the Knuth formula actually puts quite strong bounds on how your invariants can
So
behave.
that's why you formulated things in terms of included in this set of subset and
Yes, that's why I formulated that thing. So in particular, if I cannot have a copy of f adjoined u mod u to the n in the connected homology of the connected sum, unless a term of that form appeared in one of the original things, because the Knuth formula just won't generate it.
You mentioned a question about cipher fiber spaces. I didn't get it.
It's not known whether the ciphered fibered spaces generate the homology cobordism group or not. It is known that not everything is homology cobordism to a ciphered fibered space. That's a recent result of that stuff Reagan, I want to say 2014.
And there's no torsion known yet?
In theta 3z?
Yeah.
No, we don't know of any torsion in theta 3z.
There's no torsion element.
I agree.
There's no element of finite order.
We do not know of any element of finite order in theta 3z at this time. It is a reasonable conjecture held by reasonable people that there are none, although I'm not sure it's the plurality. I'm not sure it's the majority conjecture.
Amazing.
I agree. I assure you.
In terms of, if you take a ciphered fibration, in terms of the ciphered invariants, can you say something about this P? So for that homology sphere, what's the torsion look like? What's the connected homology look like?
What's the connected homology of, I'm sorry, which one do you mean?
Take a ciphered fibration.
Oh yeah, so the ciphered fibered surfaces, for the ciphered fibered surfaces, there is a simple formula for producing the connected homology involving replacing, so the Heegaard Floer homology of a ciphered fibered surface is a graded root, and there's a particular subroot that gives you the connected homology. So there's a fairly simple formula once you've written down all the parts.
You must be able to describe the ciphered fiber spaces which are homologies here.
Oh yes, certainly.
I think there's just a few, no?
Right, so yes, I agree we know which ciphered fibered spaces are homology spheres. The question was, do I know what their connected homology is? And the answer is yes.
No.
We definitely do.
I know. I mean, what is the description of Seifert fiber spaces, our homology spheres?
So you can get a description of the first homology, which is not coming to me right at the moment, but if I sat down and wrote it for a sec, it would, and then you just look for the ones where that's trivial.
Well, it's connected with the orbifold
Right.
topology.
I was just thinking it has to be 3 points and
Right.
3 indices or something.
Right.
Is that it?
Right,
Or less?
well, and then relatively, something about the relative prime,
Relative prime, yeah.
relatively prime.
Like ABC, relatively prime, like triangle groups or something.
Yeah.
In the beginning of your lecture, you mentioned that homotopy cobordisms
Yeah.
would be difficult because of relation to the 4-dimensional.
Yeah, so if I had a smooth H cobordism, so I was drawing S cobordisms as it happens, but if I had a smooth H cobordism from S3 to itself, that would disprove the point. That would answer the Poincare conjecture, because then you could sort of fill it in and get an exotic S. If I had a smooth non-trivial H cobordism from S3 to itself, you could fill it in and get an exotic S4. So like we understand H cobordisms quite well in dimensions 5 and greater, and we know quite a few things about them in dimension 4, but dimension 3 is sort of very hard. Too hard for me today, anyway.
Any other questions? It's time to speak up.